Introduction to TCP window. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this presentation, we are going to take a deep dive into one of the most critical concepts in TCP networking, which is the TCP window and the window scaling mechanism. Understanding these concepts is absolutely essential for anyone working with network performance optimization, troubleshooting slow connections, or designing high-throughput applications. The TCP window is fundamentally a flow control mechanism. It prevents a fast sender from overwhelming a slow receiver. Think of it like a bucket that can only hold so much water at a time. If you pour water in faster than it drains out, the bucket overflows. The TCP window prevents this overflow scenario in network communications by telling the sender exactly how much data the receiver can handle at any given moment. Flow control operates at the receiver side. The receiver advertises its available buffer space to the sender, essentially saying how many bytes it can accept before it needs to process what it has already received. This is different from congestion control, which deals with network capacity rather than receiver capacity. Let me walk you through the diagram that illustrates this concept. We have two endpoints in our communication flow. The sender represents the TCP endpoint that is transmitting data. The receiver represents the TCP endpoint that is accepting and processing that data. The arrow from sender to receiver labeled data segments shows the actual payload being transmitted across the network. The return arrow from receiver to sender labeled window advertisement represents the feedback mechanism where the receiver communicates its current buffer availability back to the sender. The sender connects to rate control, which represents the internal mechanism that adjusts transmission speed based on the advertised window. Rate control then connects to throughput management, showing how this regulated sending rate ultimately determines the overall data transfer performance of the connection. TCP header window field. To truly understand the TCP window, we need to look at where this information lives in the actual TCP header structure. The window field is a fundamental part of every TCP segment. The TCP header contains a 16-bit field dedicated to the window size. This field appears after the acknowledgement number and before the checksum. Being 16 bits means it can represent values from 0 to 65,535, which gives us a maximum window size of approximately 64 kilobytes. Let me explain the diagram showing the TCP header structure. The TCP header element represents the complete header that precedes every TCP segment's data payload. From the TCP header, we see it contains the source port, which is a 16-bit field identifying the sending application's port number. The TCP header also contains the destination port, another 16-bit field identifying the receiving application's port number. These two port numbers together with the IP addresses form the socket pair that uniquely identifies a TCP connection. The TCP header contains the sequence number, a 32-bit field that identifies the position of the first data byte in this segment within the overall byte stream. This enables proper ordering of received segments. The TCP header also contains the acknowledgement number, another 32-bit field that indicates the next byte the receiver expects, effectively acknowledging receipt of all prior bytes. Most importantly for our discussion, the TCP header contains the window size field, which is our 16-bit window advertisement. This field indicates how many bytes the sender of this segment is willing to accept. The diagram shows this window size connects to max value 65535 bytes, illustrating the mathematical limitation of a 16-bit unsigned integer. This 64 kilobyte maximum was adequate when TCP was designed in the early 1980s, but as we will see, it creates significant problems for modern high-speed networks. Window size and throughput. Here is where the TCP window becomes critically important for performance. The relationship between window size and throughput is governed by a fundamental equation that every network engineer should understand. The bandwidth delay product, often abbreviated as BDP, represents the maximum amount of data that can be in transit on a network path at any given moment. It is calculated by multiplying the bandwidth in bits per second by the round-trip time in seconds. For the connection to achieve maximum throughput, the TCP window must be at least as large as the bandwidth delay product. Let me walk through the diagram that illustrates this concept. The bandwidth element represents the raw capacity of the network path, measured in bits per second or bytes per second. It connects to the multiplication operation represented by multiply RTT, indicating that bandwidth is multiplied by the round-trip time to produce a result. The round-trip time, commonly called RTT, represents the time for a packet to travel from sender to receiver and for the acknowledgement to return. This is typically measured in milliseconds. The multiplication of bandwidth and round-trip time produces the bandwidth delay product, which represents the volume of data that fills the network pipe at any instant. Think of it as the capacity of a pipeline between two endpoints. The bandwidth delay product connects to the window requirement element, showing that the TCP window must be greater than or equal to this calculated BDP value to achieve maximum throughput. The window requirement connects to two possible outcomes. When the window is large enough to meet or exceed the BDP, we achieve maximum throughput, meaning the network path is fully utilized. However, when the window is smaller than the BDP, we encounter throughput limitation, where the connection cannot fully utilize the available bandwidth because the sender runs out of window space before receiving acknowledgements. For example, consider a network with 100 megabits per second bandwidth and 100 milliseconds round-trip time. The BDP equals 100 million bits per second times 0.1 seconds, which equals 10 million bits or 1.25 megabytes. You would need a TCP window of at least 1.25 megabytes to fully utilize this connection. With the standard 64 kilobyte maximum window, you would achieve only about 5% of the available bandwidth. TCP window scaling option. The solution to the 64 kilobyte limitation is TCP window scaling, defined in our FC 7323. This clever mechanism extends the effective window size without changing the TCP header structure, maintaining backward compatibility with older implementations. Window scaling works by introducing a scale factor that is negotiated during the TCP three-way handshake. The actual window size becomes the value in the 16-bit window field multiplied by 2 raised to the power of the scale factor. With a maximum scale factor of 14, the effective window can reach approximately 1 gigabyte, which is sufficient for virtually any modern network scenario. Let me walk through the diagram showing how the window scaling option fits within the TCP options framework. The TCP options element represents the variable length options field that can be appended to the standard TCP header. TCP options connects to window scale option, which is option type 3 in the TCP options numbering scheme. The window scale option contains the scale factor value, which is a single byte specifying the shift count from 0 to 14. The scale factor value feeds into the calculation shown as window field times 2 to the power of scale, which represents the mathematical operation that converts the header's 16-bit window value into the actual receive window. This calculation produces the effective window, which represents the true window size that governs data transmission. The effective window connects to example maximum showing 1 gigabyte, demonstrating that with a scale factor of 14 and the maximum 16-bit window value of 65,535, the effective window reaches 65,535 times 2 to the 14th power, which equals approximately 1.07 gigabytes. This enormous window size can accommodate virtually any bandwidth delay product encountered in practice, from local data center connections to intercontinental satellite links. Window scaling negotiation. Window scaling must be negotiated during the TCP three-way handshake because it changes how both endpoints interpret the window field in all subsequent segments. If only one side supports window scaling, it cannot be used because the other side would misinterpret window values. The negotiation is straightforward but must follow specific rules. Both the SYN and SYN acknowledged segments must include the window scale option for scaling to be enabled. Each endpoint specifies its own scale factor, meaning the two directions of a connection can use different scale factors. This makes sense because the buffer sizes and processing capabilities of the two endpoints may differ substantially. Let me walk through the sequence diagram showing this negotiation process. The client initiates the connection by sending a SYN segment that includes the window scale option with a value of 7. This indicates the client is requesting window scaling and proposing that incoming window advertisements to the client should be scaled by 2 to the 7th power, which equals 128. The server receives this SYN and responds with a SYN ACK segment. Critically, this SYN ACK also includes a window scale option, this time with a value of 8. This indicates the server agrees to use window scaling and specifies that incoming window advertisements to the server should be scaled by 2 to the 8th power, which equals 256. The client completes the handshake by sending the ACK segment, which establishes the connection. At this point, both endpoints have recorded the peer's scale factor. The connection now operates in an active state with asymmetric scale factors, meaning the client uses a scale factor of 8 when interpreting server window advertisements, while the server uses a scale factor of 7 when interpreting client window advertisements. The server then transmits a data segment with a window field of 32,768, which the client interprets as 32,768 times 256, equaling approximately 8 megabytes of receive window. The client acknowledges and advertises its own window of 16,384, which the server interprets as 16,384 times 128, equaling approximately 2 megabytes. This asymmetry allows each endpoint to advertise window sizes appropriate to its own buffer capacity. Best practices and troubleshooting. Let me wrap up with practical guidance for working with TCP window scaling in production environments. These best practices will help you optimize performance and diagnose issues effectively. First, ensure window scaling is enabled on all your systems. Modern operating systems enable it by default, but some legacy systems or hardened configurations may have it disabled. On Linux, check the TCP_window_scaling SYSCTL parameter. On Windows, examine the TCP global parameters using NetSH. Disabled window scaling is a common cause of mysterious performance problems on high bandwidth or high latency links. Second, size your receive buffers appropriately. The scale factor a system uses depends on its configured receive buffer size. Larger buffers allow larger scale factors and thus larger effective windows. On Linux, tune TCP_RMEM and TCP_WMEM for receive and send buffers respectively. Remember that auto-tuning can adjust these dynamically, but the maximum values set the upper bound. The diagram illustrates the troubleshooting decision process. The performance issue element represents encountering slow TCP throughput despite adequate network bandwidth. From here, you proceed to check window scaling, which involves verifying that window scaling negotiation occurred during the handshake. If window scaling is missing, the path leads to enable or verify support, indicating you need to check system configuration and ensure both endpoints support the option. If window scaling is present, you proceed to analyze window size, which involves examining actual window advertisements during the transfer. If windows are too small for the BDP, the path leads to increased buffer sizes, indicating you need to tune the receive buffer parameters to allow larger windows. If windows are adequate, you proceed to check for zero windows, which investigates whether the receiver is advertising zero window, indicating buffer exhaustion. The check for zero windows connects to two outcomes. Application slow means the receiver application is not reading data fast enough, causing buffer backlog. Network congestion means window reductions are due to congestion control rather than flow control, requiring different remediation strategies. For packet capture analysis, Remember that tools like Wireshark automatically apply the scale factor when displaying window sizes, but only if the capture includes the handshake. If you start capturing mid-connection, you will see raw unscaled values, which can be misleading. Always try to capture the connection establishment when troubleshooting window-related issues. Thank you for your attendance. Please consider subscribing to the channel and liking this video.